Advanced subnetting. A CCNA is required to demonstrate a mastery of subnetting. Subnetting is known for its complexity, but as with any other process, the concept becomes really simple once you have a solid understanding of the pieces involved. In this nugget, we're going to start out with a definition of subnetting. Then we will look at the reasons the subnetting is needed, followed by a discussion on the subnet mask and how it is used. And we're going to end up with a demonstration on supernetting. The definition of subnetting is to segment a classical network into smaller subnetworks. Let me give you an analogy that might help with that. Let's say that you ordered a pizza and for some strange reason it came to your home, delivery, not sliced at all, just a whole pizza. Now there's two options here. If you're serving one person could probably go ahead and eat that pizza, just start taking bites of it. You laugh at me, but I had a friend in high school that actually did exactly that. But anyway, on with our analogy. Let's say that you wanted to serve more than one person, though, that you had a lot of people. What you're going to have to do is slice this pizza up into segments that can be used by each individual. The same idea holds true when we're talking about a network and dividing it into subnetworks. Here we have an example, an IP address 172.16.0.0. This is a Class B network per our definition. Now here's the binary breakout of that network. If you recall, our default mask says that the network portion resides in these 16 bits and the host portion resides in these 16 bits. Our goal in this process is to divide the host portion into a subnetwork portion and a host portion. In other words, we're going to borrow some of the bits from this portion to be part of our subnetwork. So let me show you a realistic diagram that will illustrate the need for this. Let's say that you have a network that has routers throughout the network, and what you're going to need is 250 different local area networks or segments. Like you see here, see how this interface is off of this router? That's one. You're going to need 250 throughout your network. You have been given one Class B address, 172.16.0.0. By definition, with that default mask, we have one network that's been given to us here, and within these hosts, we are allowed 65,534 different hosts, but on one network. So in other words, this network would have to be completely flat. You could have one router, one interface hanging off that router, and then on this local area network, 65,534 nodes possible. There would be no hierarchy to this network. It'd be completely flat, as I said. So the need to divide this network is clear, but how are we going to accomplish that division? And the answer is with our subnet mask. Remember, we had a default mask, and we'd use a logical AND function to divide the network from the host? Same idea here, but we're going to use a subnet mask to divide the network and subnet portions from the host portions. Let's see how that would work. Here I have a depiction of each of the class of addresses, A, B, and C, and their default mask. A has 8 bits for the network, 24 for the host. B has 16 for the network, 16 for the host. C has 24 for the network and 8 for the host. We're going to take a Class B address for our examples and use it to break out a subnet mask, use the logical AND, and show how subnets work. So far, the main requirement of our network was that we can create 250 distinct networks out of that one Class B address that we were given. So what we're going to have to do first is figure out how do we take a portion of this host field here to make subnetworks and have 250 or more subnetworks available to us. And the answer is found within this formula right here. This is 2 to the number of subnet bits minus 2. All right, whenever we're trying to figure out number of networks that can be supported, we will start here and move in this direction as far as the number of subnet bits that we use for our count here. So let me give you an example. If we use 2 bits here, these two here, 1 and 2, we would have 2 to the power of 2, which equals 4, right? Minus 2, which gives us 2. So that means that I would have 2 subnets available if I use this portion of our original host field for a subnetwork field. And then it will go on from there. 2, let's say I use 3 bits, to the third power is 8 minus 2. That will equal 6 usable networks at this point right here within subnetworks. And we can proceed on down the line. 2 to the 4th power is going to be 16 minus 2 equals 14 usable subnets if we use 4 of these bits. Now, for those of you that don't want to do this in your head, and I don't blame you at all, we can use the scientific calculator that is found here on our desktops if you're using a Microsoft desktop. Hit in the calculator, make sure you're in scientific mode, and then simply hit 2 to the power of, we just demonstrated 4, which equals 16 minus 2, and that gives you the number of subnets that you can use by using that number of bits within the host field. Now there's another thing that you can use. It's somewhat of a quick cheat sheet. Knowing that these first 2 bits is going to allow you 2 subnets of use, a cheater code would be to double this plus 2. So in other words, times 2 plus 2 will give you the next number of subnets that can be used by using 1 more bit. So 2 times 2 plus 2 is 6. 6 times 2 plus 2 is 14. 14 times 2 plus 2 would be 30, and we can check that out on our subnet calculator to make sure that that holds true by clearing this. 2 to the power of 5 minus 2 equals 30, exactly as we had said. So when we use 1, 2, 3, 4, 5 bits to represent the subnet portion, we're going to have 30 subnets available. All right, so let's do that. Break out the binary code on that. All right, when I say I can use these 2 bits here and have 2 subnets available, this is what I'm saying. The combination or possible combinations with those 2 bits are 0, 0, 0, 1, 1, 0, and 1, 1. That's what these 2 bits can be represented as, because the only 2 states in binary are 0 and 1, right? All right, well, we have the rule that we spoke of earlier that said a network or a host of all zeros is not allowed, and a network or a host of all ones is not allowed. The same is going to hold true for subnets. All right, and this is in a general sense. So that's why we're saying you will be allowed 2 subnets that are usable by using these 2 bits. Even though there are 4 possible combinations of binary values, 2 of them are not allowed. So the same thing is going to hold true when we use 3. We're going to have 0, 0, 0, 0, 0, 1, that's 1. 0, 1, 0 is 2. 0, 1, 1 is 3. 1, 0, 0 is 4. 1, 0, 1 is 5. 1, 1, 0 is 6. And then 1, 1, 1 is 7. These are the possible values. You take this one off, and you take this one off, and you have 1, 2, 3, 4, 5, 6 possible subnets available to you. So all the math works out together. Going back to our network scenario, we needed support for 250 subnets. So let's continue on down the line. If we use 1 more bit, which would be 6 bits in total for our subnetwork, we would have 30 times 2 plus 2, which is going to give us 62. Still not enough. Let's use 1 more bit. This is going to be 7 bits in total. We'd have 62 times 2, which is 124, plus 2 is 126. Still not enough there. And finally, we're going to use 8 bits in total, and that's 126 times 2, which is going to be 252, plus 2 gives us 254 possible subnets, and we found our answer. We're going to need 8 bits to represent the subnet portion, and we'll find them here. Now, the subnet portion is going to be represented just as the network portion is when we're talking about mask. You use a 1 to represent them. So 1, 2, 3, 4, 1, 2, 3, 4. So all 8 bits are here, and this is the subnet portion of the mask. This is the network portion, and this is what's going to allow you to divide that classful network into smaller segments that are better used within your environment. So let's take a look at the subnets that are allowed using this Class B mask. Here we have the Class B that we started with, 172.16.0.0 as an address. Here we have its binary representation. And here we have the subnet bits. Now these bits are going to be allowed to change so that we can come up with our different addresses. Some of the examples are found below. All zeros would be a 0. It's scratched out because that's not allowed. Here we have the representation of a decimal 1. Decimal 2, decimal 3, and this would continue all the way to the end of our run when we have decimal 253, decimal 254, and then the decimal 255 that, as you remember, isn't allowed. So really, our range is between 1 and 254 possible subnets, and that exists in this third octet right here. Now let's look at some examples of subnets that we might have. 172.16.1.0, where these first 3 octets are the subnet portion, and the last octet would be considered the host portion. Another example, 172.16.2.0. Again, these 3 octets set aside for subnet, and here we would have the host. Within the host, we have this 4th octet that we're dealing with. We have possibly 8 bits that can be manipulated to give us our different host addresses. just so happens the same number of bits that we have within this area, which is our subnet field. So if we have 254 possible subnets, then it'll hold true if we have 8 bits in the host field that we have 254 possible hosts as well on every subnet that we create. So the results of what we've created so far could look like this. I could have a router, and it could have 2 interfaces. Out of one interface, I would have the network 172.16.1.0, and out of another interface, the network 172.16.2.0. Again, each of these with 254 possible hosts. Now what we've done so far has its own complexity. That is true, but it is also known as easy subnetting. Let me tell you why. The subnet boundary is right here, then it correlates with a bit boundary. In other words, it's pretty easy to understand that you have 254 possible subnets here and 254 possible hosts on this end. Now what's a bit more complicated to understand, or for the mind to accept, is non-bit boundary subnetting. In other words, that bit boundary could have existed here, or maybe it could have existed here, anywhere except for the bit boundary, and it makes it a bit more complicated. No pun intended. All right, let's look at an example of subnetting of this type. We're going to start out with the exact same Class B address. And this time, our need for subnets, we need 600 subnets available out of this Class B address. We don't have any concern at this point as to how many hosts. We just know we need this many subnets. Here you see a representation of the default mask that comes along with the Class B address, exactly where we started before. All right, well, we're going to figure out how many bits we need to support 600 subnets. Let's cheat a little bit. We just talked about the fact that at this bit boundary here, using 8 bits, we can support 254 possible subnets. All right, so this is, if we use the formula of the number of possible subnets in existence times 2 plus 2 to move over 1 bit, what we're going to find is times 2 is 508 plus 2 will give us 510. So not enough as of yet. Again, if we use this formula again, we're going to have 1,020, that's 510 times 2, plus 2, so that's going to give us 1,022. It is over 600. In fact, it's well over 600. That's going to be known as your room to grow in the future, and you're going to want to build that into your networks whenever you're designing networks. So this is not a bad solution by having a little bit of overhead here. So the answer to having 600 subnets with this Class B network is that we're going to use 8, 9, 10 bits in the subnet field. Now here's where it tends to make your brain swim a little bit. This is going to be the breakout of our possible range. Let me show you. All right, here we have the 10 bits that we're using for our subnet mask. And here it is here. These are the 10 bits involved in the subnet. The possible values, just as we did before, are all zeros. That's not allowed. So the first allowable value is all zeros in the 3rd octet and then a 0, 1 to begin the 4th octet. What is the decimal equivalent there? I'm going to include the whole IP address, 172.16.0.64. This is the low end of our range. In other words, this is the first available network that we can use. And it's going to proceed all the way up until you have, well, not all ones because that's not usable, but right before you have all ones, which is this representation here. Now let me write that out. That's 172.16.255.128. This is the last available network that you can use. So like I said, it's not as easy on the eyes when you're subnetting at a bit boundary, but it's not any less true than it is when you're subnetting at a bit boundary. These are your available networks, or range of networks. Let's go to the next whiteboard, and we're going to break out some of the networks that appear within that range to help us ease your mind a little bit and be a little bit more understandable. What we're going to deal with is the 10 bits within the subnet portion. In this first representation, we're going to have dot, and to start our 3rd octet, 0, 0, 0, 0, 0, 0, 0, 0, which is 8 zeros, dot, we're starting our 4th octet, 0, 1. That's why we get zeros here because of this binary number, and here we get 64 because, remember, in this last octet, there are 8 placeholders. The first one is 1, 2, 4, 8, 16, 32. This is the value of 64, and so it's turned on, so you see 64. The next value you see here is going to be, again, the 8 zeros that we have in that 3rd octet, and then in the 4th octet, we're going to have 1 0. And this value here is 128, and that's why you see it there. Next, we're going to have all zeros here. And then what we're going to do is, in this last fourth octet, combine both of these together to give us 192. Then we've got to proceed down to the next bit. Even though there's a dot there, it doesn't matter because these 10 bits are in a bit boundary. So what we're going to have with 172.16.1.0 is, again, we're going to have a lot of zeros in this octet, but not all of them. The last bit is going to be 1, as we see here. And then in the fourth octet, we're going to have 2 zeros. And we're just going to proceed on down the line, and that's the representation until we get to the end of our range. Remembering all along that each of these subnetworks can be placed on interfaces within our routers, and then you're going to have a possible combination of hosts that exist out there. So let's figure out the host. If I'm going to have 2 bits of my fourth octet designated for the subnet ID, that means it's going to leave me with 6 bits that I can use for the host ID. So with 6 bits, 0, 0, 0, 0, 0, obviously not allowed. And then if I go just to the portion where I have just 1 bit on, there it is. And then a total of 6 bits turned on is going to give me a representation of decimal 63, but again, this is not usable. So my range is going to be between 1 and decimal 62. These are the usable ranges or the usable host IDs that I can use out there for each host that's on this local area network. So I'm going to have 62 available hosts along with my 600 subnetworks that I've created here. Up to this point, we've taken a standard Class B address and we've defined it by how many networks we want to have in existence. We're going to change that around a little bit. Now we're going to define it by how many hosts we need per network. And the number of hosts we're going to need is 500. All right, so you recall in the last 2 exercises, what we did is when we want to figure out a number of networks or subnetworks to be supported, we start here and we move this way as far as our bit borrowing, right? Well, when we're trying to define it by host, we're going to do it from this end, and we're going to move towards the left for our bit borrowing. So this is the host, this is the subnetworks. All right, so let's move ahead. Same idea though, same concept. If I have 2 bits, I will be allowed 2 available hosts. And it's going to proceed exactly as it did before. 2 to the n minus 2. So this will be 2 to the 3, which is 8, minus 2 equals 6. Then with 3 bits, I'm going to have 6 available, and it's going to proceed on. So let's see. I need 500. I know at this point here, again, that I need 250, or I get 254 available hosts. If I go one more bit over and use the other formula, which is 254 times 2, which is going to be 508, plus 2, which is 510, then I am going to exceed what I need as far as available host per subnet. So I know that my host portion has to stay with 9 bits. And what does that leave me for my network? That's going to leave me 7 bits for my network. Although it feels great to have figured out the mask associated with having 500 hosts per subnet, you're not done yet because we have to assign each of these subnetworks onto a router. And right now, we don't know the number of the subnetworks. So let's move on and let's figure that out. What we're going to have is a representation of our subnet mask, and this is the new one because we have the default mask right here and then the bit borrowing that took place, and there were 7 bits left for the subnet mask. All right, so once we've completed this, we have a base address of 172.16.0.0, and we said that the first network that is available is 172.16.2.0. The reason we say that, the subnet boundary is right here, right in between these 2 bits. And because that's true, whenever you fill in this first bit with a 1 and all other subnet bits with zeros, that's going to be your first available subnet. And that one actually works out this time to be .2 in the 3rd octet. All right, so, we've had this happen once before where we could use .2, .3, .4, and so on down the line when we used all 8 bits for the subnet mask. This is going to be different, so let me demonstrate why. If we try to use 172.16.3.0, the resulting binary breakout in that 3rd octet is 6 zeros and then 2 ones at the end. All right, let's look at just the subnet portion of this. 172.16, 172.16. These are identical right here between these 2 and these 2 here. Now this one we have 6 zeros and a 1, and down here we have 6 zeros and a 1. they're identical as well. So what you're going to find out is this is a host address on this network. So 172.16.3.0 is a host address. In other words, that could be the address for N1 out on the network. It comes off of a router that's 172.16.2.0. All right, so this is not another network. You've got to be careful of that. The easiest rule in understanding this is if you look at the last bit within the subnet mask and its value, so in this case it's going to be a 2, this value is the address of your first available subnet and the value to increment by to find other available subnets. So 2, 4 is the next available address, and after that is 6. Don't just take my word for it, let's break it out. We have 172.16. Here we have 1, 2, 3, 4, 5 zeros, a 1, and a 0, which is the next logical step to having 6 zeros and a 1, right? And that happens to be the value of 4. So there you go, 172.16.4.0. That's a good subnet. Now here we're going to have 172.16.6.0. Here you see the 2 and the 4 value put together to come up with the decimal equivalent of 6 here. So now we're going to have this as our next available network. And you're going to completely jump by 2 as you go through here and find your available networks, at least in this instance here. If it had been that the bit boundary took place, let's say right here, then the value is 1, 2, 4, 8, 16, isn't it? So your first available subnet in that case would have been 16, the next would have been 32, the next would have been 48, then 64, and so on down the line. So that's the trick that you can remember. The value of the smallest or the least significant bit in your subnet field is going to be the value that you're going to jump from subnet to subnet on. Do you remember that I mentioned one of my high school memories earlier in this nugget? Well, I'm going to give you another one. Do you remember when your math teacher would give you the long form of solving a problem, and just before you thought you couldn't take any more in, they would show you the short form, and you'd think, wow, how great is that? I'm going to do the same thing, but remember, before I show you the short form, this long form that we are demonstrating here is vital to your success within the CCNA examination. You're not going to have an IP subnet calculator, but in the real world you will whenever you're doing work on your network and designing your network. So I'm going to show you how to use this specific subnet calculator. It's freeware. It should be included on the CD-ROM that you purchased from us. All right, the first thing you're going to do is you're going to make sure you're in the right class of address. What we've been dealing with so far is a Class B address, so we're good there. Now, under the specific address tab, that's where we need to put in the address that we're dealing with. So I'm going to punch in there 172.16. All right, now that we have that done, it has a reference point to work off of. And what we need to do is, if you remember our conversation before, we said we needed 250 hosts, and we decided that 8 bits within the subnet mask would get us there. Well, let's see if that's true. 8 bits in a Class B network with the specific address 172.16.0.0 is going to give you, you go to class information, and it's going to tell you the maximum number of subnets you can have, 254. On each subnet, the maximum number of hosts is 254, exactly what we had figured out before. And as a bonus, it includes this bitmap down here. It's going to give you the 10. Remember, that's the first octet rule whenever we have these default masks or these classes. Then we're going to have ends for the default network mask. Then the S is going to indicate how many bits have been borrowed for the subnet mask, and there was 8 of them, just as we had said. All right, remember the next scenario we went into, we wanted 600, let's make sure we have the same address here, we wanted 600 possible subnets, and we decided that we needed 10 bits borrowed to make that happen. Address here, bits borrowed here, go to class information, and it tells you exactly what we had found out. Maximum number of subnets, 1,022. Every subnet is going to have available 62 hosts. And then here it tells you again the breakout, and here's the subnet bits that we borrowed, all 10 of them, 2 of them in the 4th octet. And then the last thing we did was we said we have a specific IP address, 172.16.0.0, and we wanted to make sure we had 500 hosts. What we came up with is that we needed 7 bits in our subnet field. Remember, I'm not counting host bits, so even though we went from right to left in our counting to figure out 500 bits, we did leave 7 bits for the subnet side. So let's check that out. Here's the 7 bits in the subnet, and what does it say? Maximum subnets is 126. Very good information, but not what we're looking for. This is what we need. Maximum host, 510, well within our range of 500. There's one other point within this calculator that I want you to be aware of. Remember in our first example, we said we used 8 bits in the subnet field, and here we see them represented here. Well, there's another way of representing, rather than the dotted binary notation that we saw here, and that the decimal mask instead in dotted decimal notation. And this is how it would read, 255, 255, 255.0, because this octet is all ones, this octet is all ones, and so is this one. And we know that all ones in an 8-bit binary octet is going to equal 255 in decimal. All right, the second example, we use 10 bits. So the first 3 octets are the same, 255, 255, 255, and we see that here, all these ones. Then we use the first 2 bits in that 4th octet. Combined, that's a value of 128 and 64 together equals 192. So there's the binary representation, there's the decimal. In the last example we had, we used 7 bits in the subnet field, as you see them here. The last one we left for host in the 3rd octet. The decimal mask is 255.255.254.0. So this is a very important piece of information as you're reading other literature concerning subnetting. So as you can see, these subnet calculators are real time savers. What's taken us a number of minutes to figure out by hand over here took us just a couple of seconds, if you will, with our IP subnet calculator. But there's one caution. Don't let your subnetting skills get rusty. Use the subnet calculator when you have to, or even to check your work. The key is to keep the subnetting skills that you have in your mind as sharp as you can. Now, so far I've given you the calculator, but you can't take that into the exam. And I've given you a lot of great information that you can take in the exam with you, but what I'd like to do is take that information and bring it down into one easily understood area. And we're going to call that area the subnetting table. All right, let me get you familiar with the table first. We're going to have bits. The high bit, or the first bit starting on the left-hand side, is called your high order bit. Now, as you move down in your subnetting adventure, this way in the bits, wherever you stop is called the low order bit. Most of the times, octet boundaries are used to signify high and low order bits. And then we're going to have the decimal values associated with each of those bits. What we do is we start at the low order bit and we have a value of 1. And then simply we double that every time we move over to the left. So 1, 2, 4, 8, 16, 32, 64, 128. Nothing new. It's exactly what we showed you in the nugget. All right, now we're going to have the decimal mask that's associated when you borrow bits. So we're going to start on the left-hand side because we're talking about borrowing bits, right? So if we borrow 1 bit, not really a mask because it's not possible. You can't have subnets by borrowing simply 1 bit. We talked about that earlier. So you have to borrow at least 2. And the way you're going to figure out the decimal mask is you're going to find the sum of the bits associated in the mask. In other words, if I borrow 2 bits, this bit and this bit, I'm going to add these values together and come up with a value of 192. So this is where we would get, in a Class B network, 255.255 as the default mask, and then as we subnet with 2 bits in that 3rd octet, we would say 192.0 for the 4th octet. This is simply the sum of those 2 values. Let's continue on down the line. If we had 3 bits in our subnet mask, then we would have a value of 224. 4 bits would be 240. 5 bits would be 248, and then it proceeds 252, 254, and then the one that we mostly hear of, 255, which is all 8 bits in this octet used for a subnet mask. All right, well, the binary mask is also important, and really that's just an illustration of how many bits have been borrowed to come up with our subnet mask. So in this case, it would be 1, 1, in a series of 6 zeros. In this case, it would be 3 ones and a series of 5 zeros. And in here, 4 ones and a series of 4 zeros. So this would be right in the middle. Here, 5 ones, 3 zeros, 6 ones, 2 zeros, 7 ones, 1 zero, and then all ones at the end here to signify the binary mask. All right, now here's the really important part. The number of subnets that are usable when we use a certain number of bits within the subnet mask. So let's start on the left again. If we use 1 bit, none of them are usable, and that's because that's not legal. We talked about that here. All right, if we use 2 bits, our first legal option, what we're going to get is 2 available subnets that we can use. Now, the way we figure this out, the shortcut to it, is that start with 0 here in the high order bit. What you do is every time you move over to the right, you multiply by 2 plus 2. All right, so 0 times 2 plus 2 is 2, because 0 times 2 is 0. But in the case of 2, 2 times 2 is 4, plus 2 is going to give you 6. There are 6 legal subnets that you can use when you use a mask of 224 or a 3-bit mask as associated up here. All right, and then it just simply moves on. 2 times 6 plus 2 gives you 14 usable subnets there. Here we're going to have 30. Here we'll have 62. Here we're going to have 126, and we're going to end up with 254 if every one of these bits was part of a subnet mask. This next rule is very cool as well, but it comes with a caveat, and that is this holds true as long as you don't subnet beyond the 8 bits within the octet. As soon as you go out of this octet, let's say we're dealing with a Class B address, this represents the 3rd octet, these 8 bits. As soon as you subnet all 8 of those bits plus 1 bit within the 4th octet, this rule is no longer going to hold true. But most of the times you won't be doing that, so let me show you the rule because it's very, very cool. What this is the subnet breakout. And what it's going to do is identify the subnets that you can use. All right? This is the number of subnets that can be used, but this tells you exactly what they are. This is how you do it. You take the low order bit. Let's say in this case we're using 2 bits, so this would be the low order bit. You find that value. It's 64. So your first usable subnet is going to have 64 in that 3rd octet if this is a Class B address. So you'd have whatever the address is, let's say 172.16.64 as your first address. And the other thing it gives you, not only the first address, but the inter-subnet gap is what I'm going to call it. It tells you how much you need to increment to get up to the next available subnet. So not only is 64 the first value, but if you add 64 to that value, you come up with the next usable value, which is going to be 128. And so that'll be your second usable subnet. And you only have 2 in this range, as we've identified here, and those are it, 64 and 128. Isn't that just cool? I know, it's like watching TV when they have the street magician on the show, and as soon as he levitates off the ground, the first thing everybody says is, oh, do it again, do it again. I won't let you down. Here we go. Let's say that we're using 3 bits in our subnet mask. We have our value now, which is 32. We're going to use that same Class B base. We're going to have the first available subnet then as 172.16.32. Not only do we have the base, but we know what to increment by. So the next available will be 64. The one after that, 96. After that, 128. After that, 160. And then the last one's going to be 192. And it's going to hold true that we have 6 available subnets. And here they are, 1, 2, 3, 4, 5, 6, when we use 3 bits in a Class B network to subnet. And in fact, that would be true if we use these 3 bits in the 4th octet when we're subnetting a Class C network as well. It's simply knowing that we're using these bits within an octet. Once we go out of the octet, as we said here, this will no longer hold true. All right, let me finish filling in the subnet breakouts. 32 if you use 3 bits, 16 if you use 4, 8 if you use 5, 4 if you use 6, the value of 2 if you use 7 bits, and then 1 if you're using 8 bits. Now remember, this subnet table is going to be included as a document within the CDs that you receive from CBT Nuggets. So far in this nugget, we started out by looking at the definition of a subnet mask. We also looked at the need for subnetting, and then we went into how we use our subnet mask. Next, we're going to talk about supernetting. Now remember that what we just reviewed was called subnetting, and it was a matter of taking a large pie, cutting it into smaller segments so that we can use that in different areas of our network. Well, supernetting is kind of the opposite. Instead of cutting it into smaller segments, we want to take these small segments and create a whole pie again without the segments. Now this is how it's going to work. First of all, supernetting is defined first in RFC 1338. Then later, RFC 1519 came along, made a couple of adjustments, a little improvement to it, and it was known as CIDR, which is Classless Interdomain Routing. And so you're going to hear both of these terms interchanged in different literature, but they both mean the same thing, and I'm going to explain that concept to you right now. Here we're going to have a typical Class C address, 192.168.16.0. It's Class C because of the range here. 192 and up was Class C, right? And so we just fall into it. Remember that in subnetting, I had my default network here, and I had my default host here, and what I would do is I would borrow bits in this direction in the host portion so that I could come up with smaller segments of that original classful network. Well, this is going to be just the opposite. We're going to work in this direction because what you're trying to do is take an original classful group of addresses instead of just one address and make them appear as one entire address together. This is how it's going to work. 192.168.16.0, .17.0, .18, and .19. All four of these networks we're going to try to combine into one network. And the way we're going to do that, again, is by taking bits away from the network portion. So the answer here is going to be that we're going to represent our mask in the first octet with 8 ones, which is 255 is the decimal equivalent. We're going to do the same in the second octet. We're going to have 8 ones here. And then in this third octet, we're going to give up 2 of our bits over to the host field. It's these 2 bits right here. And the reason we're going to do that is we want our boundary right here before the value of 4 in this octet. Remember we talked about a helper or a cheat earlier when we were doing our subnetting. We said the least significant bit in the subnet portion, and in this case in the network portion, is going to give you an indication as to where your valid subnets exist. In this case, where your valid networks are going to exist. So if it's 4, you're going to say that 4 is going to be your first valid, then 8, then 12, then 16, then 20, and it's going to continue down the line that way. Well, look at what I'm trying to group together. 16, 17, 18, and 19. I know that 16 is a network, so that's a good start there, right? And then 17, 18, and 19 will be in that same network because they're before the next natural boundary of that network, which will be 20. So if I create my bit boundary here, and I have 6 bits in the third octet for the network portion, I borrow 2 bits to go along with the host on this end, then I'm going to achieve my goal, and I'm going to have a range of 192.168.16.1, and it's going to proceed all the way up to 192.168.19.254 for usable host, and then 255 is going to be my broadcast within this one network. So what I've done is I've taken 4 original Class C addresses, made them one network, and it's not a class network anymore. This is definitely classless. In this nugget, we started by defining subnetting as the segmentation of a classful address into smaller subnetworks or smaller chunks. We also examined the need for subnetting, and that was the fact that we had an inefficient classful system. After that, we identified what a subnet mask was and how to use it. We understood that really what we're doing is borrowing bits from the host portion of a default mask so that we can use those bits within the network side to create the subnets. And at the end, we took a brief look at supernetting so we could identify that it was the act or process of combining classful networks into one larger network rather than having separate classful networks, especially in use with Class C networks. I hope this has been informative for you, and I'd like to thank you for viewing.